So let's do some of this math right here to see what these K values are. That's the great thing about exponent math. It's so darn easy to do. Let's take a look at these boundaries here. Let's find out what the value is for the proton concentration at ice water temperature, the proton concentration when water is boiling, and compare it to room temperature. Room temperature, simple enough, square root of 10 to the minus 14, 10 to the minus 7, so the pH is 7. The pOH is 7. Now let's go down to ice water temperatures. 0.1 times 10 to the minus 14, oh, that's 10 to the minus 15. How do you do the square root of 10 to the minus 15? Oh, simple. You get to divide by 2. 10 to the minus 15 divided by 2 is 10 to the minus 7.5. Therefore, the pH and the pOH of ice water are 7.5. On the other side, when water is boiling, I've now got almost a 2 order of magnitude increase in the amount of kW. It's up closer to 100 times 10 to the minus 14 than it is to 1 times 10 to the minus 14. So this is the number 10 to the minus 12 here I'm working with. What's the square root of 10 to the minus 12? 10 to the minus 6. Oh my gosh, the pH close to boiling point is 6. So I actually have a range of pHs here from around 7.5 to around 6 for pure water, depending upon what the temperature is. So the next time you feel like getting somebody all hot and bothered, you walk up to them when they're sipping on ice water and go, oh my gosh, that's pH 7.5. Or they're sipping some very hot tea, oh my gosh, the pH is 6.5. Now, for people who understand what's going on, they appreciate a couple of things. One, the difference between pH 6.5 and 7.5 doesn't matter a whole lot in terms of drinking your drink. But more importantly, they appreciate, that's just the kW changing. You can figure that out with the Van't Hoff equation.